Topic 4, Portfolio Optimization, Section 7. Construct optimal portfolios given return targets. So in this section, we're going to repeat the process of finding 3 portfolios, but instead of having vols of 9, 18, and 27, I'm going to specify return targets your client wants, and we're going to build optimal complete or combined portfolios. So I'm going to select expected returns of 7, 5, and 8%. Now the reason I chose those is I know that one of them is on the CAL, 5%, one of them is on the CAL-B, and one of them is on the envelope. I know that because 7 is greater than the expected return of the optimal borrowing portfolio, therefore it must be on this line. 5 is less than the expected return of the optimal risky portfolio, therefore it must be on this line. And 7 is right in the middle. So 8 is greater than this vol, 5 is less than this vol, and 7 is right in the middle. So for the 7% envelope or 7% portfolio, that's the one that's on the envelope, I'm simply going to run solver, minimize vol for a 7% mean, and see what the envelope portfolio looks like. For the 5 and 8, I'm going to have to do an equation to find the weight in the optimal risky portfolio. Now, a complete portfolio return or a combined portfolio return that combines risky and risk-free assets is the weight in the risky times the return of the risky plus the weight in the risk-free, which is also 1 minus the weight in the risky times the risk-free. I can rearrange this formula and solve for W risky. The optimal weight is going to be my 5% complete portfolio desire minus RF over the weight of the optimal risky portfolio minus RF. And again, I know it's the optimal risky portfolio and not the optimal borrowing portfolio because 5 is less than the expected return of the optimal risky portfolio. For the 8% volatility or expected return portfolio, I'm going to use the same equation. I'm going to put in my 8%. I'm going to put in the expected return of the optimal borrowing portfolio, and I'm going to subtract off my RB. So let's go to the spreadsheet. The first portfolio has an expected return target. We'll say we'll do the first one of the 7%. Then we'll do the 5%. And then we'll do the 8%. So on the 7% portfolio, I'm just going to run solver, data, solver. I'm going to minimize vol. I'm going to delete the constraint on vol and add a constraint that the mean is equal to 0.07. Hit OK. Solve. Solver found a solution. As a 17.22% volatility, I'll paste that there, Alt-HVV. The weights are these 3 weights here. Copy. Alt-HVV. And it's 100% risky, meaning no combinations of risk-free or borrowing. So if the client wants the best 7% portfolio, given our little universe of 3 risky assets, borrowing, and risk-free assets, and they had $100 to invest, I'd put $54.55 into SPY, $6.81 into EFA, and $38.64 into EMA, and it should show up right here on the envelope. And we won't add it this time. I'll just eyeball that. So 17.22% looks like it would show up right there on the envelope, so that looks good. Now to find the second portfolio. The second portfolio wants a 9% expected return. That's less than the expected return of this optimal risky portfolio. Therefore, it must be somewhere on the line segment going from RF to the optimal risky portfolio. That weight, 9%, I'm going to say equals open my total targeted expected return minus RF divided by the return of the optimal risky portfolio minus RF. And that number, change that format, is 62.5% invested in the risky. 1 minus that, invested in treasuries. So I tell my client to, if they had $100, buy $37 in the risk-free asset. $62 goes into this portfolio, which is constructed by taking 62%, anchor it, times the weight of SPY in that optimal risky portfolio. Change the format and copy across. So if my client had $100 and wanted the best 5% portfolio, I tell them to put $37 into treasuries or risk-free, $47 into SPY, $15 into EMA, and they'll have a volatility of 62% of the volatility of the optimal risky portfolio, which will be 10.14%. Last one, and again, that point would be, if I come across from 5%, that point should be right around here, which is about 10%. The last one is an expected return of 8%, so it's going to wind up being around this point here. So let's go ahead and do the math for that. I'm going to take my desired volatility, or expected return, of 8 minus RB divided by 7.44 minus RB. So that portfolio is 129.13% invested in this portfolio right here. In other words, 1 minus that number is the amount of borrowing. I would take my 129%, anchor it, times the weight of SPY, IFA, and EMA in the optimal borrowing portfolio. So I tell my client if they had $100 to invest, borrow another $29 at 5.5%, and take that $129 and invest 90 into EMA, 33 into IFA, and about 6 into SPY. And if I take my 129% of the volatility of this portfolio, that portfolio will have a volatility of 27%. So it gives me a point right about here, which is 8% and 27. So these are my optimal complete portfolios for return targets of 7, 5, and 8, and optimal complete portfolios with vol targets of 18, 9, and 27. If you want more, here are some more links about this topic. So in topic 4, we've constructed optimal portfolios by constructing and graphing an envelope portfolio given 3 risky assets. We then constructed a capital allocation line that combined the risk-free asset and an envelope portfolio. We then found the CALB line that combines borrowing and an envelope portfolio. We then looked for optimal complete portfolios, either on the CAL, CALB, or the envelope by looking at their return or volatility compared to the return and volatility of the optimal borrowing portfolio or optimal risky portfolio. We then constructed optimal complete portfolios on the envelope, on the CAL, on the CALB for both return targets and volatility targets.